is going to talk about his very long quest for low latency in Linux block I/O, and we'll talk about his amazing BFQ stuff. Please welcome Paolo.
Thank you. So this talk is about latency and block I/O. Well, latency is a quite general term. So what do I mean here for latency? I mean application level and system level latency. That is, for example, how long do you wait before an application starts? In this particular case, latency measures what we usually call responsiveness. In general, responsiveness is how much does it take to execute an interactive task, such as starting an application. Another example is how long does it take to have a frame read by a video player while it is playing a video, and which translates into how many frames will be dropped during the playback or during the streaming and so on. So this is what I mean by latency now here. And we will start, I will start by reporting the last general and I think interesting developments in block I/O. And after this, we will dive into the core of this presentation, that is the serious latency and responsiveness, in particular responsiveness problems related to block I/O in Linux. Along the way, I will try to debunk a common myth that is, if speed increases, then latency will just disappear. Unfortunately, this is false. But on the bright side, I will show you a solution that seems to really work. That is an I/O scheduler called BFQ. Finally, BFQ had a really hard and long time to get into mainline, but fortunately there seems to be a happy ending, and this is what I will tell you at the end of this presentation. So, to start, here is the block layer. It just manages I/O with block devices, block storage devices. Basically, it does so by translating read and write operations into I/O requests that are enqueued in this queue here, the request queue, and are also manipulated by other, how can I say, subcomponents of the block layer. The most interesting one for us for this presentation is the I/O scheduler that is inside the block layer. Actually, there are several I/O scheduler you can choose from in the block layer, and this morning these schedulers have already been mentioned, and also yesterday. In any case, the job of an I/O scheduler is more or less the same as for a traffic policeman in an intersection. It just decides who passes, who uses the resource. And it does so to provide some useful service guarantees that typically are low latency, high responsiveness, and fairness in accessing the device. Okay, so in Linux you have these three I/O schedulers: CFQ, which is the most accurate one, the fairest one, and so the one aimed mostly at providing those service guarantees. Then there is Deadline. Okay, let me go directly to NOP, which is easier. NOP does nothing, as the name says. Deadline does something that more or less I never understood, but I don't know, we can talk about it, but really I'm not the right person to tell you what Deadline does exactly. So they are here, and okay, this is about I/O schedulers. I need to add another piece of information which is related to these interesting new developments. As you can see, there is only one queue where the requests are inserted and from which the requests are extracted before being dispatched. This queue is accessed with a global lock. This means that whatever you want to do with that queue, with those requests, you have to hold that lock, which implies that in a multi-core CPU, only one core at a time can execute block code. The code of the block layer. I'm sorry. The original block layer is is abbreviated as block, BLK. I'm sorry. So in BLK, in block, you can do only one thing at a time with only one core. So it's sequential. This was not a problem till some years ago. Why should it be a problem? Because the maximum I/O speed that you can sustain is upper bounded by the maximum speed at which one core can process I/O. So this was not a problem until some years ago, because that that processing speed was very high with respect to the speed of the devices. But now I think that this is not true at all, not true anymore, because the new very fast devices that all of you know have really changed the game. So BLK cannot make it anymore with the speed of modern high-level, high-entry devices. This is why the kernel has undergone a radical change, a move from the old good block BLK to the new block NQ, block multi-queue. As the name suggests, and as you can see from this picture here, now there is not more only one queue, but there is one queue for each core. And then you can easily understand what's the goal. The goal is executing the code in parallel on the cores. And this gives you a huge speed up. Not only that, block NQ is also more efficient. There are several other improvements. The final result is that block NQ overcomes the 1 million IOPS barrier, and it goes much higher than that. Okay, so this is block NQ. This is what is happening. Now block is, let's say, considered, at least the developer of block NQ wants to consider it legacy code. There is not such great agreement about that, but we are moving toward block NQ. This is somehow the near future. There are still several problems. On the usual mailing lists, there are, can I say, frequent reports of problems to solve, but this is normal because block NQ is, what can I say, rather young. But certainly this is probably the only way to go to handle the current high speed of storage devices, of next generation or current generation high entry storage devices. So going back to what matters for this presentation, there is no I/O scheduler in block NQ. Well, you can find an I/O scheduler in block NQ only in this picture. I don't know why Jens left it there. Jens is the block layer maintainer, but it's only in the picture, but there is no scheduler inside block NQ, no infrastructure to put a scheduler in block NQ. It's not only the absence of the scheduler, but it is no infrastructure. It's not possible at all as of now to have a scheduler, I/O scheduler inside block NQ. Well, but you may say, okay, but our problems are already solved. Speed is increasing. It will go on increasing. Latency will just tend to 0 because serving one request is extremely fast. So we will have a fantastic responsiveness, perfect video playback, and all the rest. Well, unfortunately, no. Responsiveness and latency may even get worse. So now you may say, okay, you are completely crazy. When do you finish? Well, I will try to tell you why. I didn't drink anything, but I will show you why. And since it's a little bit counterintuitive, I will show it to you concretely with 2 steps. The first step is with 2 demos on an hard disk and on an SSD, and I will show you that the problem is still with us, at least in block. Then I will show you why the problem gets even worse in block and queue, and I will use an animation for that. Actually, for the first step, I will do a little bit more than just showing the problem, because I will show you also a solution. That is this I/O scheduler, this BFQ I/O scheduler. That is currently, you didn't see it in that list because it's not yet inside the kernel. So the first demo. In this demo, we'll compare CFQ, deadline, and NOP with BFQ with respect to two performance metrics. Responsiveness, application system responsiveness, and a drop rate in video playback. The demo shows also other things, but we don't have the time to see everything. And that is where you can find the demo if you can sleep tonight. I don't know. It is good too. Okay. So the first one. Okay, this one. Okay, there you can see some details about the hardware, but basically it's a relatively fast hard disk. We can skip all of this and go directly to the beginning of the actual demo. In a moment you will see a main window. In that window, from this window, I will start repeatedly a terminal with cold caches, because that's how you get I/O involved otherwise. So here I will start this terminal repeatedly and measure its startup time. So I'm measuring responsiveness by measuring the startup time of the application. This is one example of responsiveness. So the measure time, and right below the average startup time when the disk is idle. Of course, now it's the same number because the disk is idle. It's only starting the terminal. Here I will start some background workload, because this is the interesting case. When there is some background workload, otherwise you don't need a scheduler, you just serve the request. From here I will switch between schedulers, and here you can see the list of the 4 schedulers, so the 3 Linux scheduler plus BFQ. Okay, here you can see the throughput, but this is not that interesting. Okay, so I'm about to, okay, let's start just reading just one file. And as you can see, the startup time immediately doubles, okay? And it should become a little bit more than twice the idle startup time. Now let's switch to NOP and see what happens. It happens that there are fluctuations, but okay, it's bad again, and on average it's worse than CFQ. If you check several iterations, then you see that the average is a little bit worse. And then deadline in a moment. The performance of deadline is about the same as NOP. Okay, now we are just reading one file. So how can I say, this is the minimum workload that we can imagine. It's mild workload. Things get more interesting if we start adding some heavier workload and see what happens. So let's go to 2 files. We are still with deadline, and we start to wait and wait. This is a way to have a sort of break in the presentation. Because okay, I can breathe. If we switch back to CFQ, things are a little bit better, but still you don't have the time to go there and pick a coffee, but still you wait more than 3 times the time that you wait in case the device is idle. So at this point you may say, okay, but this is normal. There is a lot of I/O going on in the background. So what do you expect? Well, I'm about to show you what happens if we switch this time to BFQ. The startup time after an initial fluctuation, because there is still the queue full with the previous request, this is the initial fluctuation, but then the startup time becomes equal, apart from 0.1 seconds, equal to the one that you had when the device was idle. So you don't even realize that there is some background workload. So let's try with an extreme workload, 10 files. Let's make this game hard. And now it will, okay, let's see what happens. Okay, you pay this 0.3 seconds. Actually, this is because this is a rather old version of BFQ. With the new version, since I'm a little bit paranoid, I have wiped out also that 0.20.3. If you switch back to CFQ, okay, this time you can really go and pick your coffee. And CFQ is the best one among those schedulers there. This has even been a lucky run because usually it takes even more than that. So while we wait for CFQ, I can tell you, I have all the time to tell you what's next. Next is the playback of a movie. Let's see what happens if we play back a movie while there is this sort of huge background workload. So I'm about to stop everything here. As you can see, I had to switch to BFQ to let that one start. And after the usual fluctuations, the startup time now will go again down to the idle value. So in a moment, I should stop everything here and restart everything from scratch, from the beginning. So reading 10 files and playing back a movie. Let's see what happens. As you're about to see, the playback will be perfectly smooth. You can see some glitches, but they are due to the graphic card and to the fact that you are here. I have recorded a video while it was being played. So basically, this was the problem, but nothing to do with the I/O. But to make things harder, let's also start the terminal repeatedly. You won't notice any problem. The playback will be perfectly smooth. Now you may say, okay, this is a rather static scene, so it's easy. But in a moment, the scene becomes much more demanding. There is a complete change, movement, and a lot of details, but there will be no problem. The first time I did this, it was not recorded, but I did it live. I won't do it anymore because at any second I was thinking, "Wow, is it true that it will work?" Okay, this time it's recorded, so I'm more relaxed. Okay, if you do it, do the same with CFQ, well, I can tell you that you will not drop any frame. No frame will be dropped. Why? Because the movie. So in a sense, CFQ is better because 0 drop rate, but no movie. Okay, this demo goes on, but I don't want to steal too much time because this time I want to show you also something else. So, okay, but I will buy a fast SSD and problems will disappear. Let's see. With an SSD, now let me jump everything and let me go directly to the results. Okay, so exactly the same test, apart from that we'll start LibreOffice Writer, I think it was, if the name was wrong, because it takes more. Otherwise, with the terminal in the idle case, you almost don't see anything. Okay, 0.6 when the device is idle, CFQ as scheduler, and in a moment, so what do you say? It will be twice or 3 times the idle time. What's your bet? Let's see. Okay, I talk too much in these demos because then it takes too much time. Okay, just one file and one file. 4 seconds, so it's, I don't know, a lot of times more. Do the math. While you wait, you can do the math. You have all the time. If you switch the knob, the situation is a little bit better with just one file. But I could increase the speed here if I. Okay. But if okay, with deadline about the same. If we go to 2 files in the background, then we are at something like 4 times, 3 or 4 times as high as when the device was idle. If you switch back to CFQ, it's better that you don't switch back to CFQ. So with this device, CFQ is worse than the other schedulers. There is a reason for that, but I don't want to. Okay, wait. Let me speed up this because I think you have understood what is about to. Just a little. Okay, those 30 seconds there. With BFQ, you pay only 0.2, 0.3 seconds. You paid them with the old version of BFQ, now almost nothing. So let's try again with 10 files, and in this case, it becomes like maybe at most twice the idle time. Again, because this is an old version of BFQ. And I just wanted to show what happens with at least one of the other schedulers. Deadline. And prepare to wait. Okay, I think I convinced you that we still have a problem. Okay, the problem is unsolved, and it's even paradoxical because with a 1 kilo IOPS hard disk and BFQ, the startup time of the application is shorter than with a 50 kilo IOPS SSD without BFQ. It will be strange. And what is the scope of these problems? Well, they become much worse if you add a writer. For example, if you copy a file, then problems really clear. I could not do a demo with writes because the machine stalled. So I tried several times, but then I had to stop the recording because I had to switch off the machine. So in the end, I said, okay, I will do a demo with only reads because otherwise it's impossible. So we have the same or much worse problems, but with less control in these other cases, compiling files, virtual machines performing I/O, software updates, daemons doing some I/O, and so on. Okay, well, going back to block and queue, so yeah, but next devices will be fast. We will use block and queue. These problems will not be there anymore. No, they get worse. I don't have time to show you a third demo. Try yourself, you will see that they get worse. So you may have this question now, why do they get worse with block and queue? But let's put these questions in order. Probably the first question is, why do we have all these high latency problems? We have devices that are becoming faster and faster. Still, we have to wait all this time. Why does speed does not solve them? And why does BFQ work? And of course, the last question. So next slides are just answers to these questions. So about the core of the problem is due to this, is related to this fact. You get the peak rate only with sequential I/O for several reasons. One is that you pay the access time to a sector, a page, a block, whatever you want. You pay that access time once, and then you get all the sector, all the track, and whatever. The other reason is that sequential I/O is predictable. So the device can be clever with it and do some pipelining and so on, because it can guess where the next request will be. So any sensible system tries to reorder requests so as, of course, to achieve maximum throughput, which means that it tries to put them in sequential order. Said in another way, it implements the elevator policy. And this is the main cause of the problem, one of the main causes of the problem, as I'm about to show you with the last animated part of this presentation. So here we have in a moment, this is our system, this is our queue, which is reordered according to the elevator policy, then there is the device, and here we have the I/O requests of the sequential. I want to say one thing. please help me. I was not good at creating a sharp video from my PNG frame. So if some of you is better than I am with FFmpeg or whatever, please help me, because this is really horrible. I know it, so I would really appreciate it. But okay, so these are the sequential requests, and then the requests of our application is starting. And these are, of course, mostly random. So okay, this is the order, then one request is served, but when the other one arrives, it cuts in front of the random request, because it is sequential, and we have an elevator policy here. And this goes on and on and on until something helps our request. Usually there is some aging timeout to avoid that that request remains there forever until the I/O terminates. So, but then it restarts again, until there is this timeout files. This is a simplification. Things can be a little bit more complicated, but that's the idea. Okay, but here is another solution. Just stop queuing inside the OS. Let the device do the queuing. Okay, use NOP. Well, the problem gets worse, because internally to the device there is, of course, another scheduler for throughput, and this scheduler has less high-level information, so it does very little about what process originated a given request, but it does know a lot about where the request is, even physically. So the internal scheduler is ineffective in reordering requests to get latency, fairness guarantees, and so on. But it is effective in reordering for throughput, which means that it is aggressive, which means that latency goes up. Okay. The other question is, so you also say that speed doesn't solve the problem. Why? Here is why. The second part of this ugly animation shows you why. So it's exactly the same setup, just the device is extremely faster. And this is what happens. Simply, the request waits for the same amount of time, just more requests goes on. But it's the same, exactly the same. So the only thing, again, that can save that request is some timeout or some other clever mechanism to try to recover from this extreme starvation situation. So in a moment, there should be that timeout, and then the request is served, and then the problem restarts from the beginning. So, and you cannot be helped by speed, you cannot be helped by your file system, you cannot be helped by any feature of your flash translation layer or whatever. So why does BFQ work? Is it magical? No, it's just that it tries to use the throughput to serve the right I/O request, the red one, okay? So it does so only if it is needed for latency. In that case, throughput may be sacrificed, but not that much, because BFQ is opportunistic. It helps latency in the most opportunistic way, so that it does not sacrifice throughput when it is not needed. So the real challenge is not providing low latency. The real challenge is providing low latency at the same time high throughput. That's the real challenge. Of course, if there is no application to privilege, then BFQ only tries to maximize throughput. Finally, the last question. Why things are worse with block and queue? Because there is no scheduler. So requests just fight for the device without any control. Okay, so last part of this presentation. So where is BFQ? It's an independent free project. You can find it here. Does it work? Well, many people have been using it over the last 6 years, and they are all happy and seems stable. Well, so why didn't you try to have it in mainline? I tried. It was rejected several times. Why? For reasons that had nothing to do with BFQ or with its performance. So meanwhile, block and queue took over. Now block is considered legacy. So this is the last reason for the reject. You cannot change block. Actually, it's a situation that I don't know how many of you have read the book Catch-22. So it's a Catch-22. The penultimate reason was, no, don't add BFQ. Replace CFQ internally with BFQ. Okay, I did it. The new reason was, I want you to replace CFQ. CFQ is in block. Block is legacy. I don't want you to replace CFQ. Back off. So this was the last situation. But nevertheless, at the last kernel summit 1 week and 10 days ago, fortunately, success arrived because Jens Axbo, Christoph Elwig, and others said, okay, no, we do want BFQ. BFQ is good. I did ask this explicitly to Christoph Elwig in the hallway, and I just said to him, okay, there is only one question here. Why don't you care about people using Linux? And he said, no, I do care. I do want you to put BFQ inside the kernel, but I want you to do it the right way. And the right way means block and queue or that. So, but fortunately, Jens Axbo, okay, he also said, yes, let's do it. And he also volunteered to do what has to be done. That is to add an infrastructure, the missing infrastructure in block and queue, to be able to plug a scheduler in block and queue. So this is the part that he will do. After that, I don't know whether it is written somewhere. No. After that, I will do my part and can I say mold the API and what needs to be changed to let BFQ really be compliant with block and queue. Okay, so how can I say? In Italy, we have a saying that reads more or less, beware of what you dream because it could come true. So BFQ would become the only I/O scheduler. That worries me a little bit. Okay, and I can tell you in another news, there will be an I/O scheduler only for single queue devices, because they say that for multi-queue devices it will not be needed. We will see, but one step at a time. Okay. Okay. So it's almost over, penultimate slide. Could you help? Yes. How? Use it. Try it. Use it. If you like it, spread the word. That's all. And this is really the end, and thank you for your attention.
Yeah, thank you for the great talk, and you definitely forced me to skip my sleep tonight. Well, it's normal. It's okay. Thank you. Yeah, I really what I want to ask you is how do you know inside the kernel what request is important? Because why is it important? Some really sequential sequential I/O that looks like sequential could be actually random, and how does it work?
I would say that if the question for Christoph was, why don't you care? The question in this case is exactly your question. How do you know what are the right requests to set? Well, in BFQ, simplifying, of course, there are two heuristics. One is to detect the interactive applications, because those are the ones you care about. And the other one is to detect the soft real-time application, which is a complex name to say video playing, audio playing, video streaming, and blah, blah, blah. So those are the two categories for which you care. So about the first one, briefly. What is the signature of an interactive application? The signature is that at a certain point it starts doing I/O and then it stops for a while. Maybe after a while it restarts and then it stops again. And this is what an application. So this is what an interactive application does, and this is how BFQ detects that it is interactive. This is the simplified version, but that's the idea. For the software time application, the application must be, as the usual name is, isochronous. So periodic, and it must remain without requests before issuing the new batch of requests. Because a video player gets some frames, then plays them back, and then gets the new one. So you must see a batch of requests, then silence, then another batch, then silence. So it must be isochronous, and it must not request too much bandwidth. Otherwise, it means it is something else. So the heuristic is tuned with reading a 4K video, the bandwidth needed for that one. Above that bound, it does not think anymore that it is soft real time. But this is something that probably, I don't know, we will have to tune it. It changes over time. So these are the two pieces.
Hello, thank you. I have a question. You told about media players terminal. It looks like BFQ is more suitable for desktop applications, right? What about servers with web server or database and something like this?
Yeah, that's another good question. So, in principle, BFQ seems good also for servers. Because, for example, with a web server, what you want to do is give the pieces of a page as fast as possible. And you get this result with BFQ because if, for example, at the same time you are, how can I say, doing some upload, something like that, which is big, then with BFQ, in any case, the small requests for the web page anyhow are read quickly. So seems good. Also, if, I don't know, you have this server, you want to access the server remotely, you want your shell to be interactive. Again, BFQ seems good. And video streaming, it's actually the same as video playback. If you are streaming a video while you are saving another video at the same time on the same device, then it is good to use something like BFQ. And some company paid me to do that. Why I say for this reason here. BFQ is a son of block, and everything is slow in block, which means that more or less with BFQ you cannot go above 30 or 50 kilo IOPS, which is a lot for, can I say, common devices, hard disks, MMCs, SD cards, even middle-end SSDs, bandwidth limited, a lot of examples. But with a server, with enterprise SSDs, so that's why the answer is yes and no. And after this hopeful merging, I think I will restart working on it and trying to understand. In block and queue, you can go faster. So that one is the right place to work on overhead because I think I know how to increase the speed. But this is, how can I say, again in my dream list. So we will see. So yes and no. If your server is below this bound here for each device, I mean, then okay, it's good for a server. If it's above, no, you use NOP.
One more additional. If we serve database, if we run database on the server and the web application, database is more about sequential or?
Database should be random, I guess, mostly random. I said random because there have been 2 or 3 sort of flames on LKML about this. Because I went on saying Jens, Christoph, and all those people that there is more about life than random I/O. But they think that all the world is made of random I/O, and database is their typical example. So yes, but what how can I say? It seems like most relevant developers in I/O focus on random I/O from database. Don't ask me why, but they say it's random.
Okay, thank you. Thank you.
Hi, Paolo. Thank you for your speech. And have you seen some steps in separating writing and reading operations? For example, there's great problem when you're flashing write buffer. Your reading operation quasi fully stopped. Do you know something new about it?
Yeah. Yes, I know this. We all know this problem. If the write back starts, you are in trouble. Very quickly, in that case, the situation is so critical that IO requests don't even get to the scheduler. They don't even get to the block layer because they are stuck in the virtual memory subsystem. I have already worked on it. I have made, with some students of mine, good students, we have made a solution, a prototype, and it works. We have focused mainly on Android system because that's a case where you see this problem very well. Then we have stopped because we were seeking support from a company that in the end did not provide it. So I froze the task. Now there is interest from the Google Android kernel team. I talked with them at the kernel summit, and it was very interesting because I thought, okay, I made this experiment with my Nexus 4 and my Nexus 6, and there is this huge problem. They say, oh, they are slow. Now we have great speeds. Try our Nexus 6P or the other new device. So, okay, I said, well, here are the instructions. Do this, this, and this. I sent this email, like 1 or 2 hours later, the reply, oh, Paolo, you were right. Let's talk about your solution. So I hope that I have convinced them to collaborate on this. And yeah, I have already the solution in my pocket, I can say. But a prototype is one thing, something that you can put in a production system. There is a lot of work in the middle.
Do it involve rewriting some kind of virtual memory backend?
Yes. Your questions are really yes. I did it for another company, which is called a virtual open system. And for them, I made a virtual version of BFQ, which is called virtual BFQ, because you may have the best possible scheduler in your guest and the best possible scheduler in your host, and latency is horrible in the guest. The reason is that when the guest needs the bandwidth, maybe the host is giving the bandwidth to the wrong other virtual machine, or I don't know, some other workload. And for Murphy's laws, it always happens this way. So for them, I made a version in which there is a coordination between the BFQ in the guest and the BFQ in the host. They talk to each other, and when it is needed, the one in the guest says, help me, I need bandwidth because I have a guy here that is starting an application, is starting his terminal, please give me the bandwidth now. And it works. So in the guest, you have the same latency as if you were on bare metal. It's quite nice. Yeah.
So you mentioned earlier that the BFQ is doing some detection of what the interactive task is, and you mentioned the virtual BFQ stuff.
Yeah.
But is there some way for user space to give some hints, or like is there some C group or namespace stuff where an application or something in the user space layer can say this is definitely an interactive application and it needs priority?
I think I couldn't have got a best result if I paid all of you, because this is another perfect question. This is exactly what we did in Android. It's the user space that tells but this is because it's just a prototype. So what do you care about when you are using your phone? You only care about the app in the foreground. So the user space tells, I'm in the foreground, help me. And so yes, and this is an example of doing this through from user space and through C groups, exactly. Yeah.
Okay, last question.
It's fantastic. I feel I'm on the presentation of completely noiseless electric jigsaw. And my question, how can I use it in kernel 4.4? Is it available in this kernel?
it is. Yeah, we have, as I wrote here, we try to provide patches for all kernel versions. So yes,
So
you.
I need to install patches to kernel.
Yes, you have to, because it cannot be, how can I say, shipped as a module, because I didn't find a good solution with Tejun Heo, which is the sort of maintainer of C groups. I told him, with another student of mine, we made the new infrastructure of C groups to actually plug in new policies, because before that it was quite rigid. So we made the flexible infrastructure so that you can add a new policy. So at that time, in our patch, there was a change which pushed up the number of possible policies. So just it was only 2, I don't remember, and it was pushed to 5 to say, okay, if somebody else wants to add a policy, there is room. Tejun told me, no. If you want to add a policy, then you provide a patch that changes that line. But to change that line, you cannot have a module cannot change a line of an either file. So for that reason, you cannot have BFQ as a module, and you have to patch your kernel.
So I need to visit some site and
Yeah. Or if you have the right distributions, you already have it, because several distributions like Mageia, Manjaro, Arch Linux, OpenSUSE, I don't remember all the list. Ubuntu too, for Ubuntu there is a package, Debian there is a package, so if you have the right distribution, then either you have a package or it is already the default scheduler, or there is some instructions to have it. Otherwise, yes, go there, patch your kernel, recompile, and all the rest. Yeah, thank you.
Thank you, Paolo, for amazing talk today.